Hello, everyone. Welcome to our SIAM FME seminar. It's a great pleasure for me to introduce our speaker, Stephane Crepey, today. Stephane is a professor of mathematics at the Université de Paris, and he is in the laboratory for probability statistics and modeling there. And Stephane has done many sort of significant contributions, and his research interests are in the area of counterparty credit risk, XVA analysis, risk measures. He's also been doing lots of work on central counterparties, simulation, machine learning techniques, uncertainty quantification, and model risk. And I think that talk today is exactly in this direction. He has authored numerous research papers and also two books. One is Financial Modeling, a backward stochastic differential equations perspective, and the other one is Counterparty Risk and Funding, a Tale of Two Puzzles. And Stephane is associate editor of the SIAM Journal on Financial Mathematics and also the Journal of Computational Finance. He also serves as a member of the Scientific Council of the French Financial Markets Authority. And it's a great pleasure, Stephane, to have you here today. And the talk will be on Darwinian model risk and reverse stress testing. So the floor is yours. Thank you.
Thank you very much, Ludgard. And this is joint work with Claudio Albanese and his former student and now JP Morgan, Stefano Iabichino. So part is published in Risk Magazine, part is rewritten in the form of a more academic paper, and part is in this working paper, reverse stress testing. So the context is the evolution of, say, industry practice regarding models since before the global financial crisis of 2008, where banks were mainly doing trade-specific pricing using more and more high-quality pricing models, more refined models, fine-tuned to specific products, to the necessity for banks since the crisis to compute different metrics at the portfolio level or at the net income level, including CVA, for instance, which banks are doing with lower quality models because these things are big and much more demanding in terms of computation time. So this coexistence of different models of different quality led the FRTB to put an emphasis on model risk, okay, which is of course an old topic. It's commonly defined, and you can find roots of this definition in Derman 96, as so model risk would be quantified as a difference between the intrinsic value of an instrument and its model price. And we'll see if this is a good definition, and if it is enough in particular, or if there is something more to the topic. So what do we call Darwinian model risk? It comes from the consideration that the good models are the ones that are econometrically more realistic and require less recalibrations over time. And however, the number of bad models are persistent on the market. So we wanted to understand why and how. So the thinking is that in order for a bad model to remain in use for a long time and affirm itself as a market standard, it ought to satisfy two conditions. So the first one is related to competitive pricing. So this is the first Darwinian principle. A lower quality model surviving the test of time must make the trader more competitive on the market. So it must overvalue products which are bought by the bank, so that the bank is proposing to the client a higher price, and it must undervalue products which are sold by the bank. Otherwise, the trader is missing the deals and the banks make no volume. But this initial mispricing in favor of the client, in fact, means that the bank is losing money on the valuation side of the portfolio. So this first principle raises a profitability puzzle. How a systematic valuation alpha leakage, so losses on the valuation side of the position, can be sustained over long time horizons. So this leads to the second Darwinian principle, that a surviving lower quality model must generate gains on the hedge side of the position, which surpass the systematic losses on the valuation side, at least in the short to medium term. But the hedging side of the position is mark to market. So it's a martingale under the fair valuation model, under the true model. So systematic hedging gains on the hedging side can only be the compensator of a negative jump, a loss in the future. So here, what this picture is showing is gains, losses on the valuation side, apparently more than compensated by gains on the hedging side. But on the hedging side, gains means that ultimately there will be a loss. And so that in total, the bank is effectively losing money and is also at risk of these kind of events of explosion of the strategy of the trader. So let me give a very simple toy example, very concrete example, where the fair valuation, so the true model that the market is using, would correspond to this jump to read model. So stated under some martingale measure. So this is kind of Black-Scholes component. And then at the first time of jump of driving Poisson process began, there is a negative return of the stock by minus 100% of where it was, which means the stock drops to zero. And then it stays to zero forever because the dynamics are multiplicative with respect to S. And here I compensated the Poisson so that this is a martingale as it should be under a martingale measure. And let's say that in this background, a trader would use Black-Scholes with implied volatility in his trading. And let's say more precisely that this trader would short, would take a long position. So the trader would buy a vulnerable put, meaning an option with payoff positive part of K minus ST, indicator tau didn't occur before big T. Tau is the first time of jump of the Poisson. So the bank is buying this vulnerable put, and as a hedge, static hedge, the trader is shorting a vanilla put. So before the jump to in, because the trader is using Black-Scholes with implied volatility of the vanilla put, the trader assigns the same value to the option that he bought and to the one that he shorted as the put. Okay, because the Black-Scholes model doesn't see the possibility of the jump to in, which means before tau, the PNL, the hedged PNL of the trader is simply zero. Okay, and if at tau less than big T, the vanilla put, if the default, if the jump to in occurs before the maturity of the puts, then at the time tau, the vanilla put takes a value of K, okay, while the vulnerable put expires worthless, okay, which means at time tau, if before the maturity, the trader experiences a negative PNL, so loss, by the amount of K. Okay, so the PNL process is simply zero unless tau occurs before big T, and then there is a loss of the trader by the amount K. So the connection with my discussion before is that I can formulate this PNL process in this way. So this is a Dirac mass at time tau. Okay? And here I'm simply writing, instead of writing simply K, okay, I'm saying K minus negative drift lambda K dt plus positive drift lambda K dt. And this negative drift lambda T dt is alpha leakage on the valuation side of the portfolio. So this term is here because the trader is buying this product, this vulnerable put, at a price which is too much. And then we have an exactly compensating drift on the hedge side, which is this guy, so that the end result is that there is no drift at all. It's only a loss at time tau. Okay, so we see effective valuation, loss on the valuation, apparent compensation by the drift of the hedge, but this is only drift of the hedge, which means the drift of the hedge compensates a jump in the hedge, and the total result is in fact a loss for the bank and also a big risk, because this loss takes the form of a big negative P&L at this random time. So we see that this model risk derives from the cumulative effect of daily recalibrations, which correspond to this drift, okay? And they feed into the first moment of returns. We have DT terms here, which means that common risk measures like value at risk or expected shortfall or maybe stressed value at risk, they would not detect this kind of drift because they focus on higher moments of return distributions and also on short time horizons, whereas these drifts only develop on longer time horizons. So the only way to see this risk is to simulate the hedging behavior of a bad model within a good model. So now I will come to a less toy example, and what we in fact are targeting in the paper, which is a case of structured products where a bank is buying convexity long-term, such as 30 years from investors, so buying very long-term structured project options with the purpose of selling out of the money hedges, which are trading at a premium in the market because they are used by some third parties for their risk management. And in the case we'll be considering in a minute, the model risk will be related to callability features. So this structured product that the bank is buying to a client is callable for the bank. So the bank can call it early, which makes the product even more attractive for the investor because callable products means the product is paying higher coupons to the client. Okay, and Risk Magazine reported that end of 2019, $70 billion national of these kinds of a particular of these products, so range accrual, had to be unwound by the industry at very large losses by banks. Okay, so let me present this range accrual. So here's a picture that the bank is buying a claim where the bank will start making money only if some underlying interest rates leave the corridor. Okay, so in the first months or years of the product, the bank will not make any coupons, but maybe later rates will become either negative or maybe very high, and then the bank who bought the product will start to make money. And then the bank is selling as a hedge digital swaptions which are struck at these gray nodes. Okay, which means if the rates are becoming at some point negative, for instance, then the bank will pay money on the hedge. Okay, and if it was not for callability of the product, this would be a perfect static hedge. Okay, so all the model risk in that case comes from the fact that the product is callable, and the value of this callability is model dependent, and there is a model risk related to that. Okay, so we will examine this under the lens of two competing models. So the champion, the one which would be, let's say, the most popular on the market, would be a one-factor Gaussian model with deeply negative, with potentially deeply negative interest rates in the future. And as a challenger, and in fact, a more refined model, with a two-factor model with mostly positive interest rates and with a stochastic short-term, long-term skew. So looking at the product from the champion viewpoint, the digital swaptions that the bank is selling as a hedge are very valuable. So the bank, on the basis of this model, can sell the hedge for a lot of money because in this all-white model, when you reach interest rate zero, there is a big probability that rates can go even lower. And this means these swaptions that the bank is selling as a hedge are worth a lot of money. That's for one. So that's good because the bank is selling the hedge at a high price. The other thing is that from the viewpoint of the all-white model, of the champion model, as long as the bank, as the rates are in the corridor, the trader who hedge the claim this way is gamma positive. Right? So this is reinsuring because it means if there is suddenly rates very volatile, etc., the trader would not lose any money. So it means it looks as a dream trade, and that's what should ring a model risk bell. Okay, so let's look at it more closely. the all-white model is in fact implying higher hedge ratios and higher prices than the challenger model. Okay, so what you see on this picture is the number of digital swaptions that the bank should be selling at each of these. So this is upper boundary, as you see, at each of these nodes that I showed before. So these are the numbers of these digital swaptions that the bank must sell as a hedge, each of these nodes. So this is this number of swaptions here as specified by the Gaussian model, whereas the more refined model says a bank, you should sell much less digital swaptions as your hedge. Okay, and this is the same graph regarding the lower boundary of the domain. Okay, and then this is the pricing function, let's say, of the product, okay, of the range accrual, seen in the two models. So the Gaussian model is saying a higher price than the more refined model here, and in fact the price of the Gaussian model is only in one dimension. So we have time dimension, and then in the Gaussian model you have one risk factor. So this is, it looks to be 3D, but this one is in fact constant in one directional space, whereas this one is really 3D, okay, because this is the price of the product in the more refined model, which has two risk factors. And most important is the color code here. So red means positive gamma. So you see that seen from the lens of the naive model, okay, in the corridor, the trader is gamma positive. Whereas if you look at it from the view of the more refined model, you don't see any red here. You just see blue. So in the more refined model, it's a two-factor model. So gamma means the covariance matrix, okay, and blue means this covariance matrix is not definitely positive. It means from at any of these nodes in the corridor, okay, there is at least one direction of risk. And in fact, we are showing by these hairs the directions of risk, which means if we are here in the corridor, if the market moves in this direction in the two-dimensional space of the two risk factors in this model, then the trader will in fact lose money. Okay, and he doesn't even see it if he only considers the Gaussian model. Okay, he's not even aware of it. So, seen from the more refined model viewpoint, the product should be called earlier. In fact, the naive model, the champion model, delays the call by the bank, okay, till the point where in bad scenarios, the swaptions that the bank has sold as a hedge are become very valuable, and the bank is ultimately forced to close the position at a very large loss, okay, which is what we are depicting here. So we are showing a portion of the phase space where if the market goes along that path, this is the loss that the bank would be making by unwinding the position, and the bank would be forced to unwind the position because at some point the Gaussian model would no longer calibrate to the market. It would not calibrate to the realistic model. So to summarize the example, we are in a situation where delayed exercise decisions and overvaluation for low level of interest rates approaching zero lead to situations where trade unwinding results into substantial losses by the bank. Okay, and these losses are not dividends, not coupons. They are not. They are not swap coupons, nor credit losses, nor funding losses. They are really model risk losses. And as opposed to credit and funding losses that you can, let's say, manage through reserves. So I'm thinking of CVA, LVA, these kind of things. There is no established framework for reserving against model risk losses. Okay, so basically the only meaningful course of action would be not to use invalid models which lead to recalibration risk under stress scenarios. Which takes
Stephane,
me, yes.
We have one question
Sure.
by Sam. Sam, would you like to ask it yourself?
I suppose looking at this question of bad models more broadly, why is it that you're sort of ignoring the costs of implementing a complicated model? I'm just thinking people still use Black-Scholes for various things, and no one believes Black-Scholes is a good model, but it's very, very simple. It's very easy to use. It's easy to get a regulator to understand. And it just seems that's a big part of the story of why these models continue to thrive. I was wondering why you're not interacting with that question.
Well, in the case I presented in the beginning, the vulnerable put, in the toy example, but these structured products obey to the same logic. Using Black-Scholes, you understand why a trader would use Black-Scholes, because in the short to medium term, it would give the feeling that it is good, but in the end, you made a very big loss. So the story that we are concerning in this talk is that people don't use Black-Scholes or any other simple models simply because they are simple, but also because there are some Darwinian biases to use them so that traders make short, medium-term benefits, but this comes at the cost of long-term risk. So I'm not saying we should not consider the implementation cost of implementing a better model. But what we want to emphasize in this talk is that there are some bad models for simple models to be there. Sure, they are simple, that's good in a sense, but there can be some dangerous pitfalls.
Thanks.
In fact, what we will do later in the talk is quantifying the cost of using actually a bad model. So which is not the cost of implementing a good one, but the cost of this risk that this analysis is revealing. So the second part of the talk is reverse stress testing. So in a sense, it's a slightly different topic. The condition is as follows. So most model risk methodologies are backward looking. So people are looking what would have happened to their strategy if Lehman repeated itself tomorrow. So they look at which events went bad in the past, and they apply it to their strategy to see what would happen. And if nothing bad happens, they conclude that things are fine. Why fixing their strategy if it's not broken, more or less? So what we are advocating is that one should anticipate. So what we want to do, on top of what I showed before, is complementing the state space analysis of the first part of the talk by a quantification of the probabilities of the extreme risk events. And what we are proposing is a forward-looking reverse stress testing methodology based on long-term intensive simulations. My point here is that what I showed before, so that this here may be okay if it's not such a complex situation where you have two risk factors. So you can do state space analysis, scrutinize your pricing functions, etc. But if you want to apply the same kind of analysis to your, and I'll come to this later, CVA, for instance, which is also a topic for model risk, but which is subject to maybe tens of risk factors, or FVA, which is subject to thousands of risk factors, it's clear that you cannot just examine your state space and draw any conclusion, because you will not see anything, because the space is so large. So we have to find some more systematic way of identifying the problems. So we need a metric, that we can compute and which would reveal the problems. So we are basing our approach on a rigorous FVA, KVA treatment. The idea being that ultimately one has to maximize, I mean, the bank is supposed to maximize shareholder value. Even funding strategies are targeted to this ultimate objective, which justifies our choice of a metric in this context to be the KVA. So let me recall what KVA means. We are considering a certain P&L, big L, whether this big L is market risk, as it was in my structured product example, where I had this P&L arising from the confrontation between the product and its edge. And the edge was not perfect because sensitivities were computed with a bad model. So I had model market P&L if you want. But L could also be counterparty credit risk P&L, like with CVA, which cannot be hedged. So you have a P&L, or a funding risk, which cannot be hedged either, at least only very partially. So that would be another source of P&L. And then we want a risk measure to assess the risk of that loss on the variable. And the question number one is, under which measure do we want to do our computations? In this situation where we have a combination of risks which can be hedged and some risks which are unhedgeable, like funding risk. And so a bit inspired by the insurance literature. So this paper by Divik, which was revisited by Arsner and co-authors recently. Okay, we are considering a financial sigma algebra B, which is only a subset of the full model sigma algebra A. So A accommodates an hedgeable risk as well. And we work everywhere with the probability measure, which we denote by R, like regulatory, which is determined by two conditions. So I refer you to the paper for the proof. It's not a difficult proof. I mean the paper by Arsner, for instance, which says that there is a unique probability measure R, which conditional on B should equal a reference risk neutral measure Q, which is defined on B. So, and which, sorry, R restricted to B should be equal to Q, and R and the physical measure should coincide conditionally on B. Okay, so just two extreme examples. In the case of a bank that will not be hedged at all, then our measure will be the physical one, and the loss of the bank will be the unhedged P&L of the bank. In the opposite, and in fact, unrealistic case of a bank that would be perfectly hedged, this is not possible because credit risk, funding risk cannot be hedged by a bank. But let's say just, okay, as a limiting situation, then L would be 0, and our measure would be the risk neutral one, which makes sense in both cases, just to show that at least in two extreme situations, this choice of a measure makes sense. And then, okay, we have this L, not only random variable, but actually process, because this P&L is a process. Okay, it starts from 0, and then there are some gains and losses. So it develops as a process. We define economic capital projections as expected shortfall of the losses of the bank accumulated between time t and time t plus 1, and that economic capital of the bank at time t, okay, which is this, in that case, this white curve. So you start from fact time 0, where your P&L is identically 0, so this Dirac measure, and then time passes, P&L develops the process, and that this white curve is like a term structure, a profile of risk of the bank. And then time 0 KVA is defined as this quantity here. So if it is only a function of time, we don't even need expectation here because this is deterministic. But basically what this means is that the money that the banks need to remunerate the shareholder of the bank for the risk in the future at some sustainable hurdle rate H. So this is the logic, okay? And KVA will be our metric, okay, on which we will identify, in fact, stress scenarios. Okay, so the idea is so we do it on a simulation basis. So we do, in fact, nested simulation. We need nested because we need to sort of price, in the future, not only now. Okay, so think of a 20K outer pass developing over 50 time points, and from each of these 20K times 50, which is 1 million nodes, outer nodes, we would launch 1K inner pass, which makes it 1 billion simulation nodes, simulated thanks to GPU. Okay. Then we would compute the time zero KVA of the bank, but not only that, but also KVA scenario differentials. So for each scenario omega, we would compute their impact of the KVA, which means the difference between the KVA with and without that scenario. And then we will identify the scenarios which with the greatest scenario differential KVAs, and we would drill down the scenario, checking which points on the identified trajectory are points of extreme risk and why, etc. Okay, so seen reverse stress testing, that's what it is. Okay, done in this way. I mean, can be seen a bit as a third stage of evolution for mathematical finance. So pricing is about the calculation of risk neutral averages, interpreted as cost of replication. Then we have risk measures, which calculate expectation in the tail of the losses that arise due to imperfect hedging. And what we are doing here points out to impact on risk measures of individual scenarios, of if you want, the differential of risk measures with respect to scenarios, except we are not, I mean, we didn't push the mathematical idea of doing that, which would need to be defined. In fact, we are doing it on a simulation basis where everything is finite and discrete, and we can always define this kind of caveat scenario differentials. And what you obtain is this kind of let's say outputs of the analysis where what these dots are showing are times in months and corresponding value of, in that case, US dollar interest rates, okay, corresponding to points on a higher dimensional trajectory of various risk factors, okay, where the simulation identified extreme risk, let's say, okay. So this picture is not showing the big picture of the simulation, just showing some how do you say two-dimensional slice of the picture by saying, okay, all these dots emerge out of the 1 billion node simulations as scenarios where after 100 months, which is 8 years, okay, and for a level of interest rates, which was 50 BPs, here the bank experienced a very big risk. Okay, and then we can go to the, we can analyze in more detail what happened. And basically, you can distinguish two kinds of points. Okay, these like this one, okay, where interest rates are high, and these where they are very low. And obviously, what happens is that these points with these ones with low interest rates and big risk for the bank probably correspond to systemic risk, meaning these are points on the low side of the economic cycles where the whole economy is in recession, basically, which means credit in the model is bad, okay, and therefore in the model you have this negative correlation between credit and rates. So every situation is bad for everybody, in particular for this bank. Rates are low, and this bank is suffering a lot in these scenarios. Whereas here, the bank is having problems, even though interest rates are high, which means these are idiosyncratic extreme risk scenarios for the bank. related to the peculiarities of the portfolio of this particular bank. And why is it interesting and actionable? Because it means there is a chance that the bank could hedge at least these guys at a reasonable cost. So I'm not talking about locally delta hedging, because we are talking about kind of extreme scenarios. So we should work more about what does it mean hedging these guys. But the idea is that one should be able to hedge these guys at some reasonable cost. Whereas these guys, it's good to know they exist, okay, but hedging them would obviously be very costly, because there is a strong presumption that risk would be there for all market participants at the same time in this case. Okay, and okay, time is passing, so I will skip that. The point here is simply that this reverse stress testing methodology that we propose, being based on models, also embeds model risk itself. Okay, and what the next 3 slides are showing is how to deal with model risk associated to this way of performing reverse stress testing. So, and basically that's also a connection with the first part of the talk, because this is the same picture as before, except this one was done on this product that I showed with a good model, the 2-factor model, whereas this one was done using the bad model, the Gaussian, the white model as interest rate model. And then what you clearly see is that if you do the reverse stress test analysis with the bad model, the stress test scenarios which emerge from the analysis are very unrealistic, because the bad model is telling you, be careful, what could happen is that in 2 years, you have interest rate like minus 2.5%, and that's where you are in danger. And also look, if you pass the first 5-6 years, you are fine, no more risk. So on this basis, basically the story that we should just invalidate the bad model and only keep the good ones. Okay. So I'm skipping it a bit quick. Okay. So again, what are the applications of these kind of methodologies? You can distinguish systemic versus idiosyncratic stress scenarios. You can maybe hedge the idiosyncratic stress scenarios in the sense of long-run hedges that would reduce cost of capital, to reduce your KVA, quite different in spirit from short-term delta hedges. Okay. And in fact, you could also draw interesting risk analysis regarding, let's say, credit limits, because you can also, the same way that you are looking at scenario differential KVA, you can look at client differential KVA. Okay. Who are the clients which are contributing the most to your KVA? Okay. Or you can, and also you can replace the KVA metric by the FVA metric, and then the same way that KVA metric allows you to manage your capital, in fact, and your cost of capital, you can use the same approach with FVA as a reference metric to manage your liquidity risk, which becomes a particularly important issue with the new interest rates. I mean, the post-LIBOR era, where banks are in trouble with the management of their liquidity risk. Now, a few preliminary thoughts about what we call additional valuation adjustment. So this is not in the paper. This is still as a draft. And it is this follow-up paper I was mentioning in the beginning, which consists in revisiting Burnett's risk magazine papers of hedging valuation adjustment in the direction of model risk. So Burnett basically introduced HVA as the present cost of future transaction costs of your hedging strategy. So more broadly, what we do is we say, okay, if the bank was only using the fair valuation model for every purpose, the P&L of the bank would be a martingale. However, because of sure, transaction cost is true, but in the first place, model risk, the P&L is not a martingale under this measure R that I it was used before. And basically, HVA should be a value process for that P&L process. Okay, so compensator, if you want, of the P&L. Okay, accounting again, maybe for transaction cost, that's fine, but in the first place for model risk. Okay, but this is not enough. The thing is that it's not enough to, let's say, have a reserve for model risk computed by expectation of future P&L. Okay. As soon as there is a risk and that there is reserve, the reserve should be risk adjusted, which means one should also account for the contribution to the risk and to the KVA of the bank of the fact that the hedge is bad, etc. So not only an HVA, not only an HVA which is already enriched with respect to Burnett HVA, because it's not only transaction cost, but it's model risk in the first place. So not only an HVA, not only a model risk HVA, but a risk-adjusted HVA. And the total we call AVA. And we call it AVA because at some point the regulator had this notion of additional valuation adjustment meant as a reserve against model risk and meant as a caution to make the total price a prudent price. Okay. So now back to this vulnerable put example I showed in the very beginning. So this example serves two purposes. One, it's a kind of toy model of these much more complex structured products that you can only address by simulation. Okay, but the second purpose is that on this toy example that I gave, I can do analytical computations. I have formulas for everything. Basically, I can compute my economic capital as a formula. I have a formula for the KVA, for the HVA. So, and there is no Burnett friction KVA because it's only a pure static edge, so there is no transaction cost here. So we have closed formula for everything. So these graphs are just reflecting the analytic formulas that we have in this paper. So what the first graph is showing, so this all depends, of course, on the default intensity of the driving Poisson process, so lambda, okay, with let's say 1% as a reference here. Okay, and it also depends on the maturity of this put. Okay, so blue is 1 year and red is 100 years. 100 years for a put may look strange, but if you think that this put is in fact representing these big structured products or a CVA or an AVA, then 100 years makes sense actually. And what you see is that first of all, just to give orders of magnitude, so the base price of the put, okay, is like 10% of the strike K. Fine. And then we see that HVA, which is model risk HVA, okay, here, let's say, can be like MTM itself, 10 to the 0, which is 1. So far from negligible. It means it's a product which is worth MTM like, so strike would be 100, MTM would be 10, but HVA would also be 10. So model risk HVA would be 10, okay? Or maybe, okay. And then risk, so KVA related to this HVA risk would be again 10 or even maybe more, okay? So it means the sum of the risk adjusted HVA, so the AVA, is maybe 3-4 times more than the price of the product itself. Okay, so just to show that these model risk, well understood model risk, is in fact a huge risk. And this is of course in a very extreme case because this story of vulnerable put statically hedged by vanilla put is it's a bomb basically. It's a bomb in terms of model risk. But still, I think these numbers are quite interesting, and so you can look at the formulas which are behind, which are quite instructive. Okay. So, conclusion, the overall message of the talk is that banks should only rely on high quality models. Okay, and this is a conclusion to in fact, the three parts of the talk. So how to incentivize the use of high quality models by traders? Because the problem is that traders, their short-term interest is to switch, to go to models which gives them better results in the middle term, so big bonuses, etc. So to avoid it, one should forbid upticks. So excluding model switches where a trader says, okay, that's a good model, I know, but too complicated for my trading, so let me go to this other model. So if going to this other model means the trader is now more expensive, this is suspicious, okay? Because when we are falling in this Darwinian adverse selection model, which I explained in the talk. And if your trader tells you, don't worry, I go to this other model because it's more convenient for me, but don't worry, I'm putting the price difference between the two models in the reserve, so we should be fine. Actually, no, because if we, then the reserve should be risk adjusted, okay? And then the thing is that risk-adjusted HVA computations are very demanding numerically, right? Because what you have to do is to simulate the hedging ratios of the trader in the future, which means to do it well, you have to dynamically recalibrate the trader's model in a simulation setup, okay? Which is not necessarily totally out of scope with the help, in particular, of emerging machine learning fast calibration tools. But however, again, the best practice would clearly be that banks only rely on high quality models so that such computations are not even necessary. And what one can also say is that if banks were going into this process of computing risk adjusting reserves, as we saw from the graphs, okay, which are telling you that the risk adjustment can be 3 times larger than the reserve itself, it's rather clear that the conclusion of all that would be that charging these risk-adjusted HVA reserves would have the same end effect than forbidding upticks in the first place. So these are the references, and thanks for your attention.
Thank you very much. That was a great talk, Stephane. If you have any questions, please, you can either post them in the chat or you can just ask directly. So if not, maybe I just ask a question. So in your reverse stress testing exercise, you're sort of trying to identify extreme scenarios, right? And then you will find many different extreme scenarios. And I was wondering, do you have some sort of cutoff in terms of what probabilities, how likely they have to be that you consider them in a sense? I mean, they will often...
I mean, as you noticed, I mean, this reverse stress test part of the talk is really methodological. I mean, it's a simulation engine. So what we advocate is to consider a certain tranche of percentiles of the worst KVA incremental scenarios. Okay, we are not saying the worst of the worst because they are themselves, you know, untouched by a kind of model risk on this methodology itself, okay? But you would scrutinize the scenarios leading to KVA differentials being, I don't know, maybe 99 and 9.5 quantile or something like that, okay?
Okay, thank you. And you had some scenarios which were essentially more idiosyncratic type events, and some were more systematic type events.
Yeah. I mean, what is idiosyncratic basically are scenarios of extreme risk because of the of what the bank has in its portfolio. Okay, so this bank would have this kind of products, okay, different from the others. And that's why in this particular case, the bank is suffering a lot, even though the economy is good. Okay.
Okay, thank you.
I had a question. So regarding your conclusion that banks should only use high quality models, could we potentially call for another compromise? Like if somebody were to use your methodology to identify high risk scenarios and then adopt a method of risk adjustment that prioritizes those scenarios in some sort of way, maybe that could be a compromise between just having to do risk adjustment or choosing a simpler model.
So, well, I guess it would be better than nothing, right? So I take the compromise.
Yeah. Thank you.
Stephane,
Yes.
so one of the criticisms around the GFC, if we go back there to 2008-9, was that we had all these models that were too complicated to understand and not complicated enough to actually work very well. And you seem to be advocating that what we should do is make more complicated models which would work better.
No, because I mean, the idea is that people know what are the good models actually. I mean, they know what are the important risk factors, etc. So it's not because people are not using them, not because they don't know what they should be, but mainly for bad reasons, actually. There is this notion of fair valuation. Apparently, the way it works, there is a consensus on fair valuation. It's not to say that people don't know what are the risks, etc. The reason, the way traders depart from that is by saying, look, sure, I agree, and fair valuation, but this model is too complicated for me, too heavy, I mean, too long, too slow. So let me use this one, but don't worry, I will put the price difference in your reserve. So don't worry. So basically, the message of the talk is that this is not enough, because the reserve should be risk adjusted, and then it would reveal, the true risk of this mispractice.